Hello. In this video, we're going to look at information that we can get about the graph of a function based on the first and second derivative. So essentially, the first derivative test and the second derivative test are what we gain from looking at intervals of positive and negative values for the first derivative and second derivative. So the first derivative tells us the intervals of increase and decrease for a function, which allows us to find minimum and maximum points. So basically, if the first derivative is negative, it's because the slope is negative. So the function is decreasing. It could be a straight line, like what I've gone here, although normally our functions will be curves. So the curve could look something like this, or it could look something like this. But the point is the function is decreasing. If the derivative is greater than 0, so in intervals in areas where the derivative is greater than 0, the function is increasing because the slope is positive. So I could have just a straight line growth, but more often we'll have curves. So those curves could look something like those things that I've just drawn here. But the point is the slopes will be positive. And in a place where the function has a 0 derivative, so where the derivative is 0, where it crosses between decreasing and increasing, these are called stationary points. So it is neither increasing nor decreasing at this point. And then normally we would consider this to be a minimum or a maximum. If I think about what's going to happen here, my slope is going to be 0 at that point, or a minimum maximum. So either the function has gone from increasing to decreasing, in which case I generally have a maximum, or it has gone from decreasing to increasing, in which case I normally have a minimum. So second derivative is going to tell us about concavity, so the curvature. And that will allow us to find points of inflection. So where the second derivative is negative, we have a downward concavity. Now, this can be downward concavity with a decreasing function. It can be downward concavity with an upward function, but the curvature opens downward. If the second derivative is positive, then we have an upward concavity. And again, that can be upward while decreasing, or it can be upward while increasing, but the curvature opens upward. I think about it as if something were to fall into it, if it's downward concavity, like water would not be held in this curve, whereas if it's upward concavity, water would pool into that curve if it were raining on top of it, for example. And where the second derivative is 0 is where we will usually have inflection points. So it crosses from one type of concavity to the other. So from, say, a downward concavity to an upward concavity, this would be an inflection point. Or from a downward concavity to an upward concavity to a downward, that could be an inflection point. So that is typically where the second derivative ends up being 0. So let's look at what that looks like in a specific example. Now, this is a cubic function, and we already kind of have a sense of what cubic functions are going to look like, but we're going to determine specifically the intervals of increase and decrease. We can use the first derivative to find the coordinates of any minimum or maximum points, and then through the second derivative, we'll figure out where is it concave up, where is it concave down, and where does it inflect. Now, again, based on what I already know about cubic functions, I'm kind of expecting it to look like that. The cubic function generally will have those wiggles. It may or may not. It might just have a single inflection point. But this one is definitely overall decreasing. So I already have a sense that it's going to have one interval of decrease to start, and then another interval of decrease to finish. That there is also going to be an interval of increase in the middle. So I'm expecting to find a minimum value and a maximum value. I can see the upward concavity to start and the downward concavity to finish, so there must be an inflection in the middle there somewhere where it switches. But I can find more specifics using these tests. So the first derivative, dy dx, is going to be negative 3x squared plus 6x. And I need to find, in order to figure out intervals of increase and decrease, I first find the zeros. So the zeros of this function can be found by factoring. So negative 3x times x minus 2. So my critical values here, critical values are where this is equal to 0. So I have critical values at x equals 0 and x equals 2. Critical values would also occur at any non-permissible values, but we're going to look at what happens where the first and or second derivative doesn't exist, or even the original function doesn't exist. So non-permissible values of either the function or any of its derivatives. Those are also critical values, but we're going to look at those a little more in depth in class. So for now, we'll just stick with critical values are where the derivatives equal 0. And now I'm actually going to look at a sign table. So I'm going to look at this and say, when x equals 0, when x equals 2, the function is stationary. Based on what I already know, I'm expecting to find a minimum at 0 and a maximum at 2, but I don't always know that information to start, and this sign table will help me to figure out what's going on. And I look at the signs of the specific factors. So negative 3x and x minus 2. So negative 3x will be positive for values of x that are less than 0, and negative for values of x that are greater than 0. And x minus 2 will be negative for values of x that are less than 2, and positive for values of x that are greater than 2. So overall, the derivative will be negative, so the function will be decreasing for values less than 0, increasing for values between 0 and 2, and decreasing for values greater than 2. This matches what I expected to see, so that's good here. It confirms. And I can see that at 0, then I have a minimum, and at 2, I have a maximum. So I can now answer the first part of this question. My interval of increase, there's just one. This is increasing on the interval 0 to 2. I'm going to say x is an element of 0 to 2. It's decreasing on the intervals negative infinity to 0 and 2 to infinity. Notice that the 2 and the 0 are not included in these intervals because at 2 and 0, it is neither increasing nor decreasing. At 2 and 0, it is stationary. So I have a minimum at x equals 0, so the coordinates at that point would be 0, negative 2. And I have a maximum at x equals 2. So when x equals 2, I've got negative 8 plus 12 minus 2, so I've got 2. So those are my minimum and maximum points. Now I move on to concavity, which means I need the second derivative. So d squared y over dx squared equals negative 6x plus 6. Again, I can find critical value here pretty easily by factoring, so negative 6 times x minus 1. So that tells me that for my second derivative test, I have a critical value at x equals 1. And again, I'm going to go to a sign chart. So at 1, my concavity is 0. So at 1, it's neither curving upwards nor downwards. It has sort of a flat concavity, which means at 1, I'm expecting to see an inflection, a change in concavity. If there isn't a change in concavity from one side to the other, then that's something different. And again, we will discuss that in class. For basic polynomials, it is going to be what I expected to see. I can already kind of tell. I'm expecting to see an upward concavity on the left and a downward concavity on the right. But let's verify by looking at the various factors. Now I am going to include the constant because it is negative, so it's going to impact the sign. Negative 6 is negative no matter what the value of x is. And x minus 1 is negative if x is less than 1 and positive if x is greater than 1. Which means overall the second derivative is going to be positive, so upward concavity if x is less than 1, and downward concavity if x is bigger than 1. Exactly what I expected to see, so that's good to know. So I have upward concavity for the interval from infinity to 1, and I have downward concavity for the interval from 1 to infinity. Again, 1 is not included in these intervals because at 1, we do not have upward or downward concavity. We have a 0 concavity, so sort of a lack of curvature basically at that point. And because there is a change of concavity, we have an inflection point when x equals 1. So we have an inflection at x equals 1, and just going back up to my original function, when x equals 1, I have the point is 0. So that is our inflection point. So that would actually allow us to make a much more precise sketch than just the basic idea. So I know that, for example, at 0, -2, I'm going to have a minimum. At 2, 2, I'm going to have a maximum. And at 1, 0, I have an inflection. For this one, I'm not going to worry too much about what the x-intercepts are, but I'm expecting then to see this. I have sort of a switch in concavity there, and then here's what I have. So that would be a more precise sketch than just my general idea, but it does match what I expected to see from this polynomial function.